Alright, so let's talk about the microreaction. And I had a semester, particularly when this video got posted, where I had a student that was asking me a lot of questions about like really digging through the key, and I really appreciated that she did it. Helped me to better understand how to explain a lot of this. So I have previously done the microreaction. This is kind of a follow-up to explain it more in depth. So the microreaction is an incredibly powerful reaction, and what you're doing is you're creating a carbon-carbon double. You're creating a carbon-carbon bond, and you're doing this with diketones that are separated by a single carbon. And the reason you need these diketones is that you're trying to create resonance stability, and it creates a highly acidic hydrogen that if you add a hydroxide to it, will deprotonate. Now, for the microreaction, all we're doing is adding to this double bond. This is something I wish I had seen a lot sooner when I made the videos, because this is a lot easier way of thinking about it. So if I gave you HX, so I just gave you this double bond and I said, we're not going to say anything about it, we're just going to say that this is an HX addition. And ignoring reactions here of the ketone, you would tell me, well, I would add HX to the double bond, and I would add it symmetrically because of the Markovnikov's rule. Here's the thing. X in this case is this really big carbanion. And X is always going to add to the end of the double bond. It's going to add to the part of the double bond that's furthest away from the carbonyl. The reason here is that it's sterically hindered. So we don't have to worry about Markovnikov or AntiMarkovnikov. If we had a methyl group here, we would still have a methyl group here. We wouldn't be adding this group to that because, again, this isn't being driven by carbocation stability. It's purely a sterically hindered reaction. Markovnikov, AntiMarkovnikov assumes that there's no steric hindrance associated with the reagents that you're using. So for the first step of the microreaction, what we end up doing is that, and it's just an HX addition, where X in this case happens to be our diketone. And when we get done adding it, we'll end up adding a lone pair or carbanion to the carbon that's most adjacent to the ketone. This is also partly due to resonance stability. That lone pair can kick over, form an alkylic side, so we do get resonance stability. That's the microreaction in a nutshell. You have a double bond with an adjacent electron withdrawing group. We do an HX addition across that double bond where X is this big molecule, and we're done. So next video, Robinson annulation. A lot more to this than I originally thought, but thank goodness the student that reached out kind of asked me a lot more questions to help me articulate it. So what happens next will depend on what these groups are attached to these carbonyl carbons. But if they are methyl groups, we run the potential of doing a Robinson annulation, and there's a lot more to it than I had in my original video.